Hello all, welcome to the next part of this tutorial. In the earlier discussion, we looked at an example of obtaining the analytical solution for a one-dimensional Gaussian and then a multi-dimensional Gaussian. Okay. Now, similarly, this is a standard recipe that we have. So you can take it for any distributional form and then obtain the results. Okay. So here we have considered the continuous distribution. Now let's take one example of a generalized discrete random variable that was initially started discussed in the class. So, and the final answer we know, we still need to just look at the overall process once and then try to understand it is exactly similar in terms of the recipe on how did we did the continuous random variable case. Okay, so now let's go ahead with that. We are taking the example 2. Generalized discrete random variable. Okay, now let's consider z takes value, the random variable z takes values a1 till am. Okay, and then with probabilities p1 till pm. Now that is in this particular distribution z, a1 occurs with the probability of p1. Similarly, so on am occurs with the probability of pm. Okay. So now what do we have? Now we have given data is from is in the data is from data is in the form of IID realizations of this random variable. So what is that we have to estimate? So we need to estimate pi. Okay. Now here, see, please see here, I indicates parameter. Pi indicates a parameter, so it's not any density or thing. Okay. Now in this, what I mean by that, it's not px given by whatever those things that we are referring. It is just a simple mass. Okay. So yeah. So now, and then not only that, the parameters should satisfy. You cannot have any random parameters, okay, any random values. The parameters should satisfy conditions like now pi should be greater than or equal to 0 for all cases. And then I is equal to 1 to m. If you take them, that will be 1. Okay, that also needs to be taken into consideration. Okay, so now what do? We transform this into one hot representation. Now, why do we need to transform this? All those things has been discussed. Now we look at this transform as a function of random variable. Okay. So now for our estimation of parameters, we represent the discrete random variable z by an m dimensional vector random variable. Okay, we represent it as an m-dimensional vector random variable. Now let's call this new random variable as v. Okay, now this v takes m possible values. Okay, m possible values. Now what are those values? Now 1, 0, 0, and then 0, 1, and so on till it takes m values, and there is a very interesting condition in this case. Okay, now in which let's say that v is some value, let's say v1 till vm, any vi that I consider is either 0 or 1, and then if you sum over I is equal to 1 to m vi, this is 1, and this kind of representation is what is known as a one hot representation. Okay, this is a one hot representation. So now how does the mass function for PV is nothing but P1 V1 into P2 V2 into, there is no comma here, into PM VM. See, now you need to understand that one of these VI will be 1. Okay. Now others will be 0. Okay. Anything raised to the power of 0 is 1. So we will get whichever is actually 1. Let's say that PI VI is 1. Then the whole thing will be boiling down to PI. Now this you can write it as a product of I is equal to 1 to M PI VI. Okay. Now here this PI is representing the mass of the thing, and then this VI, which element is 1, is what it is representing. Okay. So I assume that the notations are comfortable. Okay. So now what we have now, given IID data, okay, now we have D, which is V1, V2, so until Vn. See, against our standard, again, at least against my standard notation, I am representing these instances with capital. Now, because I'm representing the values of inside each of these vector with small, so I don't want to confuse that. So I'm representing each instantiation of this random variable with capital. Okay, so that's a notational thing. So any vi that is there will be a vector of what form? vi1, vi2, so until vi m transpose. Any Vij, now this is ith example's jth component, okay, is belongs to 0 or 1. and then you sum over all j. J is equal to 1 to m. Vi j is 1. See, I is for the example, the instantiation, and j is for the component. Okay, I'm maintaining that notation now, because of which my mass function for a specific instance vi will be a product j is equal to 1 to m pj to the power of vi j. Maybe I need to just take it one line down. Okay. Superscript and subscript, please look at it. Now what is that I have to do? Now this is for one point. Now I have to consider all the points and then take the log likelihood, the standard recipe. Okay. Now considering all data points, and taking log, the log likelihood will be the summation I is equal to 1 to n ln of p vi. Okay, this is nothing but summation I is equal to 1 to n ln of the product of j is equal to 1 to m pj vi j. Okay, so log of products can be, we know how to take care of it. I is equal to 1 to n, j equals 1 to m wij log of pj. Okay, now this is the form. Now what I should do, so now I should take the derivative, partial derivative with respect to the parameters, and then equate it to 0. So but there is a problem now. See, this is an unconstrained maximization. Now what do we want is a constraint maximization, and then now why? No, because now pj, for which I'm actually the parameters which I'm interested in, now they cannot take any random values. Okay, that are there in R. Okay, it has to satisfy some condition, right? So now let's make note of this. The above formulation that we have, the above formulation is an unconstrained maximization. Correct? It's an unconstrained maximization. We need to perform ML estimation for the parameters for which there are certain constraints. Correct? So now we need to perform MLE of the parameters over some constraints, over the constraints what are those constraints? Pi should be greater than or equal to 0 and j equals 1 to m pj equal to 1. Okay, now because of which, now how will my constraint optimization look like? Okay, therefore the constrained optimization problem is max of Pj summation I is equal to 1 to n summation j is equal to 1 to m Vij log of Pj such that the summation over this equal to 1. Okay. Now, but we have two constraints, right? Each of them has to be greater than, each Pj has to be greater than 0, right? I'm leaving it as a small exercise. Now just optimize, I'll optimize only with this. You add the second constraint and also optimize. Now then what will happen? Have a look at it. Okay. So now this is a constraint optimization problem. Now you can have one constraint, two constraint. So now what do? You get a Lagrangian of this optimization and then you take the derivative of the Lagrangian and then equate it to 0. That's this procedure now. Okay. So now the Lagrangian for this problem is given by summation I equals 1 to n summation s equals 1 to m. And just to indicate that these are dummy variables, so V I S ln of Ps plus Lagrange multiplier lambda 1 minus the constraint that we have x equals 1 to m Ps. Okay. So now what is that we have to do? Now we have to calculate the partial derivative of the Lagrangian with respect to the parameters and then equate it to 0. Okay, so now calculate the partial derivative. Calculate the partial derivative of the Lagrangian and equate it to 0. Okay, that's what we are supposed to do now. Now then what will happen? You take the, okay, let's take it with respect to Pj. So now take it with respect to some Pj or Ps in this case. Now for whatever Pj that you are considering, for that it will be Vis divided by Ps. It will become minus lambda is 0 and then there will be a summation with respect to I is equal to 1 to n. Correct? So now this will be summation over all the examples I is equal to 1 to n Vij divided by Pj minus lambda equal to 0 for all j equals 1 to m. So it's for all j. It's finally it will be a parameter vector. Now if you get this, now Pj equals 1 over lambda summation I is equal to 1 to n Vij. Correct? So now what is the value of lambda? Okay, now we have to use the constraint and then look at it. Now we use the constraint. What is the constraint? If you take over j equals 1 to m Pj, it has to be 1. Correct? Therefore, J is summation j is equal to 1 to m 1 over lambda and I is equal to 1 to n Vij equal to 1. Now this I can rewrite it as lambda equals summation j equals 1 to m. See, lambda is independent of I and j, so I can take it out. Okay, I equals 1 to n Vij. Always we can interchange the summations, right? Now let us interchange this. Now, this is summation I is equal to 1 to n summation j equals 1 to n Vij. Now that means for a given vector I, you sum over all their independent individual components. That's what you're doing in this. For a given vector I, you're summing over all its components. See, if you sum over for a given vector m-dimensional vector, one of them will be 1. So this has to be 1. Now, therefore, this will turn out to be n, right? Now, this is 1. Now you add 1 n times, so this will be n. Now therefore, the value, now putting all of this together, Pj star will be 1 over n summation I is equal to 1 to n Vij. This is what, and okay, j is from 1 to n. J is 1 to n. This is the parameter vector that we will be getting. Okay, there is one value, so similarly you will get it as a vector. Now this is crystal clear, right? The final ML estimate for a given Pj is fraction of times the j value actually occurs. Okay, which makes total sense with our intuition. Okay, so now this is how we solve it for a simple generalized discrete case. Okay, so with this we conclude obtaining of analytical solutions for MLE estimate. Now we will proceed with some other interesting ideas in coming tutorials. With this we conclude this tutorials. I hope it was informative. Thank you.